Okay, yeah, so I'm going to talk about linear time proof systems, and the reason for that is that linear time is sort of the boundary that's as fast as you could possibly imagine the prover is. And we have some proposals, theoretical proposals for linear time proof systems. And the question I want to think a little about here is, I mean, will they sort of make it from theory to practice, and will that be the proof systems of tomorrow? So the background for this talk is that it basically there were three things on my mind. One is a new proof system that I've been developing with Jonathan Bootle and Alessandro Chiesa from Berkeley, UC Berkeley. So that's what we have on the left-hand side. So you'll see a tensor standing for tensor codes, tensor queries, which we use in the proof system. The other thing on my mind was recently we had the ZK proof workshop, which is about standardizing zero knowledge, and it's a great place to get theoreticians, practitioners, users together. And then, of course, the third thing is the theme of this workshop here, blockchains. So I will try to address the three of them under the heading of considering linear time proof systems and the practicality of linear time proof systems. Right, so one of the things that blockchains give us is, in my mind, trustworthiness, right? And that's what's exciting about blockchains. We have many different disciplines coming together to provide trustworthiness in an environment where people do not necessarily a priori trust each other. So that involves some game theory, that you have to create incentive structures that reward honest participation. It involves distributed computing and getting consensus even when there are network failures. And then it involves some cryptography, which we call magic, because I think in many cases, cryptography does seem like magic in terms of what you can do with it. One example being key exchange. Who would have thought that you could have two people in a room shouting to each other and agree on a secret and that nobody else knows, right? That's magic. So let's look at what is the magic of zero knowledge proofs, right? So let me compare with strawman technology. So let's say we have spot checking of a set of data samples, right? So you have a set of data samples. One of them may be faulty, and you want to check whether there's a faulty sample or not. And you could open a few of the samples, right? And if you find a faulty one, then you know that there was something wrong with the batch. If you don't find one, then either you didn't catch it because you didn't open enough, or maybe it's a clean and good batch, right? And it's clear that the probability of finding a fault decreases the more unopened samples are left over, right? And this is very typical of all technologies that are typical of some performance frontiers, right? So this is the performance frontier for spot checking a set of data samples, right? And if we compare that with the zero knowledge proofs, right, then zero knowledge proofs comes right up in the top right corner, right? Because zero knowledge proofs gives us soundness, which means that you cannot cheat at all, right? So we don't know that, if we use zero knowledge proofs, that everything is good and as it's supposed to be. And at the same time, they also provide privacy, which means that they leak no information whatsoever, right? So you don't have the problem that before with sampling, that you had to open some of the samples and actually see what's inside and lose privacy that way. With zero knowledge proofs, you don't lose privacy at all, right? So it sort of gives us the best of both worlds for free. So if you have a person who's familiar with spot checking, right, and familiar with that technology, then zero knowledge proofs would seem like magic because it completely moves the frontier of what you can do. Okay, so let me just very briefly introduce those who are not familiar to zero knowledge proofs with what it is, right? So typically we look at some binary relation. So think of a language in NP, right? So there are some instances in that language, and they have matching witnesses in the relation. Okay, so an instance and a witness may be in a relation. In that case, the instance X we consider good and part of the language defined by this relation. Okay, and the question that you typically have in a zero knowledge proof system is, well, here's an instant X. Does it have a witness? Is it in the language defined by the relation, or is it not? Right, and the prover claims that it is, okay, but the verifier does not know. So a proof system then has algorithms for, maybe it has a setup algorithm that generates some setup, and then it has algorithms for creating proofs, and it has algorithms for verifying proofs. And you can imagine the prover then gets as input the instance X and the witness, right? So the prover really knows that it's in the relation, everything is good. But the verifier only knows the instance X, right? And does not know the witness, which may contain confidential data and be something that the prover is not willing to reveal. So the idea is now that the prover can use the proving algorithm to create a proof and send it to the verifier, and the verifier can check the proof and say, okay, now I believe that there is a witness. I believe the instance X belongs to the language. Okay, now I just draw one error and one proof here, but we also have interactive proof systems where many messages go back and forth. So the prover sends a message, the verifier responds with a challenge, the prover sends another message, the verifier sends another challenge, and so forth until the prover sends the final answer, and then the verifier checks everything. So we want three properties from a proof system, okay? One is that it should be complete. So if there's an honest proof that has a witness, it should be possible to convince an honest verifier, right? So that just means that the proof system works. The other property is that you should not be able to cheat the verifier, right? So if the prover is trying to cheat but has a fake instance that is not in language, it should be impossible to convince the verifier. And those two properties together make what we call a proof system. Okay, so that's basically a proof system is an interaction between a prover and verifier that enables you to assert that a particular claim is true or whether it's not. Some proof systems then also have an additional property, namely that there's zero knowledge. Okay, and if it's a zero knowledge, it means that the proof does not reveal anything about the prover's witness. Okay, so that gives us privacy, right? And if you have those two together, then you get both soundness, but you get it for free because you don't pay anything in terms of privacy. Okay, so zero knowledge proofs have found a lot of applications in the blockchain domain, right? And the reason for that is that blockchains, a priori, there's no trust between participants. If it's a permissionless blockchain, anybody can come and join and do stuff on the blockchain, right? So it's great to have some way of actually proving that, you know, this is correct action, this is a correct action, this is a correct action. And at the same time, there are applications where you actually want that to be zero knowledge, where you want to preserve privacy, right? So you have many applications, privacy coin, you have solvency proofs where an exchange can prove that it has a positive balance, it's not bankrupt. You can have identity management. So the classical example is you could prove that you're, you know, over 18 years old, but without revealing your exact age. Supply chain management is a really popular area where a lot of effort is going into how to build that. And I think it's not, one should not see that as only zero knowledge proofs being something that helps blockchain and can be used in blockchains. I do think it's a symbiotic relationship, right? Because the zero knowledge proofs we have, they also derive value from the fact that, you know, there's so many public things in a blockchain, right? Everybody agrees on that. Everybody sees what's on the blockchain, right? And now you can start proving things about them and connecting them, right? So if you know something about different pieces of data on the blockchain, you can start proving things about them and tie them together. So I really think that both zero knowledge proofs help blockchain and blockchains help zero knowledge proofs. Okay, Okay, so I wanted to mention ZK proof. It's a standardization effort. So the idea is to standardize zero knowledge proofs and everything related to zero knowledge proofs. So people have been looking at standardizing interfaces between zero knowledge proofs, applications of zero knowledge proofs, particular types of zero knowledge proofs, benchmarking of zero knowledge proofs, and lots of other things. But for me, the value is also a lot of other things. I mean, the systemization of knowledge papers that survey different areas of zero knowledge proofs. And it's a great place for gathering researchers, practitioners, users together. And it showcases a lot of applications of zero knowledge proofs, right? And if you want to see more applications of zero knowledge proofs, that would be the place I would go and look, because there's a lot of presentations with different applications that people have been working on and are deploying in practice. Okay, so let me get a little more concrete, right? So the kind of statements that you prove could be both of a very general nature. So here's a 3-set formula, it's satisfiable, or here's a graph and it has a Hamiltonian circle that visits all the vertices just once. And these are NP-complete problems. So in principle, you can reduce any computation to those kind of problems, and therefore it shows that they're really versatile in general. You can prove anything with zero knowledge proofs. But that kind of reduction would have a cost, and people are also very interested in zero knowledge proofs for very concrete statements, right? So here's I own some coin and I want to spend it, but I want to be private, so I'll use a zero knowledge proof to prove that I own a coin, I want to spend it, and then because it's zero knowledge, it will not reveal which coin I've spent. Or you may want to cast a proof in a voting protocol. So this is how I got into zero knowledge proofs. I was working as a PhD student on secure voting. And there you have systems where it's really important that people cast valid votes, because otherwise the system breaks down. But of course, you don't want people to reveal which vote they cast, right? So the zero knowledge property is really essential here, that you can prove you've cast a valid vote without revealing which candidate you voted for. So in this talk, I'm going to talk about a popular class of statements called arithmetic circuit satisfiability. So we have some finite field. And the question, so it has addition gates, it has multiplication gates. And the question is, given some inputs, so in this case 2 and 5, can we find sort of like complete the inputs? Can we find inputs for the rest of the input wires such that the output is 0? Okay, and in this case, you could input 0 as the third input, and you would actually get 0 out. So this is an example of a satisfiable circuit. So the reason arithmetic circuit satisfiability is popular is both because it's NP-complete, so it really is a general thing. Also because in cryptography, we do a lot of operations over finite fields. So like naturally speaks to that and works naturally with the types of proof systems that we have. And also people have now found sort of like very efficient ways to reduce all sorts of statements to arithmetic circuit satisfiability. So when we talk about a zero knowledge proof system, we're interested in various efficiency parameters. Some of the important ones are how many messages do you have to send back and forth? How many bits do you have to transmit in total? How much computation does the verifier have to do? How much computation does the prover have to do? Okay, there are other parameters that are also important. Memory consumption could be one of those, but these are the ones that have typically been the things that we care the most about, right? And in the old days, cryptographers talked about things that, if it was polynomial time, it was efficient, it was great. But nowadays, that's not the bar, right? We've come a long way. And state of the art right now is that we can do proofs that are non-interactive, so it's just one message from the prover to the verifier. The communication can be as small as a kilobyte, even for very, very large statements and instances that you want to prove. And the verified computation can also be extremely efficient, a constant number of exponentiations in some group or something like that. And then the last one, that's sort of like the frontier now, is how much computation does the prover have to do? And the best you could hope for would be that you could do, essentially the prover does not have to do more computation than it just takes to take the witness and evaluate directly, right? But most schemes today have an overhead. So some log-n factor or something like that on top of the prover's computation. There are some schemes that are say that they are linear time, but then you have to look at what are the operations that they use. Okay, so let me take as one example snarks based on pairings, right? So so you take an arithmetic circuit with n gates and over a field of prime order p, where p is a lambda bit prime. Okay, and in snarks, when you say that the prover uses a linear number of operations, the operation you use is exponentiation, right? And there are ways you can do efficient exponentiations, but you typically end up with paying for each exponentiation something like lambda over log lambda or log n field operations to compute the operations in the group. Okay. So the true cost of the prover in this kind of, for this kind of instance is actually lambda times the cost of evaluating the circuit directly, right? And I would claim that that's not linear, right? But of course, depends a little on what you see as your unit of computation. But when I'm talking about linear here, I'm really talking about, I would like to have strict linear time. So if it's a circuit with n gates, and it would cost n field operations to evaluate it. And I would like the proof to have the same cost, like n O of n field operations. Okay, and we have a recent work that does exactly that. So it has a logarithmic number of rounds, and then it has root t of n field elements in communication and verifier computation, right? So so t here could be any constant integer, right? So t could be 2, then it's square root n field operations. If t is 3, then it's cube root, and so forth. So that quickly, as t grows, becomes very small. Okay, and then the prover computation is a linear number of field operations, right? So the unit of computation is the same as for the arithmetic circuit. Both of them are measured in field operations, and you pay here a linear number of field operations. So in other words, you just have a constant factor in the overhead. Okay, the related work, so it's not the first one to get linear time. The first one was a work we had in 17. But there the cost for the verifier was square root, the communication cost was square root n, and the cost for the verifier was linear in the circuit, right? So that's what we're improving here and making much smaller, to the point where it really doesn't matter much compared to the size of the instance. Okay, so I'll look a little into this proof system. Okay, so one of the things I've learned from the ZK proof workshop is that it's very common to split zero knowledge proofs into a front end that processes what you really want to prove and translate that into some intermediate form. And then you have a back end that's sort of like good for handling that. So in our case, that would look like, you have arithmetization that takes whatever statement you want about, a program does a particular thing, would translate it into something called a rank 1 constraint system. If you don't know what that is, think of this as arithmetic circuit, because it's a generalization of arithmetic circuit satisfiability. And then we are essentially working on the backend side here. So we have some something we call a proof system with tensor queries. And we use that to reduce something called an interactive oracle proof. Okay, and then you could take that interactive oracle proof and you could use hash functions, prove it secure in the random oracle model, and get a non-interactive proof system out of it. So let me just very briefly talk about what is an interactive oracle proof, right? So you have the prover. The prover can say, look, I want to prove a statement. So let me commit to a message consisting of a bunch of field elements. Okay, and then the verifier says, okay, great, you've committed to that, so here's a challenge. And the prover will say, I'll respond to your challenge by committing to another set of field elements. And then the verifier will say, here's another challenge, and they'll go back and forth a little. And at some point, the verifier will then say, okay, great, now we're done, and I'll look at those messages that you sent, those committed messages, I'll query them, and based on that, I'll decide whether to accept or reject the proof. Now, the point here is that actually those messages are going to be too large for the verifier to read all of, right? Because we want the verifier's cost to be really, really low. So the verifier doesn't actually have time to even read all of those field elements. But what we're saying instead is that the verifier can make some queries to those messages. And one example of a query would be a point query, where the verifier can query and say, look, I want the third field element in message 1. And another one is a tensor query, where you can take a bunch of vectors. So take t vectors, and t is this constant, right, that we wanted root t cost. So that's where the t comes in. And you can tensor those queries together. So basically, and then you can get the inner product with the message that has been sent. Okay, so that's sort of like you get like a structured linear combination of a message. Okay, that's what you can query for, and that gives you some more power, right? Because you can sort of like access all of the field elements at the same time. Okay, but the challenge is, of course, how do you actually make that practical and feasible for the verifier? Okay. Okay, so the first part of our proof system, and I'm not going to go into the details, but Jonathan is going to give a talk, prepare a talk soon, and he will give all the details, and we're also going to put this on ePrint. But the key point is just that you can think of committing to these messages, these bunch of field elements you want, as sort of like a cube, right, with dimension t-dimensional cube, right, with k field elements along each dimension. Okay, and then you can make a tensor query that sort of like corresponds to saying linear combinations on each of the dimensions and get out that inner product. Now, one part of our work is creating this interactive oracle proof for tensor queries. Another one is to go from tensor queries to point queries, so basically being able to translate those. And then there are known ways to translate interactive oracle proofs with point queries to standard proofs. Okay. Now, the key point I want to highlight here, I don't want to go into the details, but it's just that the way we do this is actually by using error correcting codes. Okay, so you take a code, a linear code, and you apply that on each dimension on this cube here, and that gives you a tensor code of the message that you had sent, right? And for us to have efficiency, we want the code to have constant rate. So n should not be too much larger than k. And it should have constant relative distance. So if there are errors, it should be very easy to detect them. And then you should have linear time encoding, because we want the prover to run in linear time in the end. Okay. So great. All that works out, and Jonathan will give the details in his talk. Okay. So now we have this very efficient proof system. We have linear time prover computation, and root T communication, root T verification, right? And we go to the practitioner who says, look, here's a great proof system, right? What do you think? And the practitioner will, of course, say, look, that's great, but you have this big O notation. What are the constants hiding in here? And it turns out that, you know, there's something hiding in there, right? So, and the way you can see that is just think about a tensor code, right, of a message, right? It's going to be larger than the message itself, right? Because you do this, you apply a code to it, so you get the expansion from K to N along each dimension, right? So overall, the overhead is N divided by K raised to the power T, right? And this is why we want T to be a constant, because we want this thing here to be a constant, right? So if this is a constant rate code and T is a constant, then all this is a constant. We don't care so much. In practice, they will actually be big, and practitioners will care about them. Okay, so this is sort of like all bringing me down to this discussion of linear time, right? So when I started out, I said, look, you know, true linear time, we shouldn't have exponentiations and all that kind of stuff, right? We should really be counting the units of operation and so forth, right? And now we have a theoretical proof that really has true strict linear time, right? And all the other things are good as well. We can get non-interaction, we can get low communication, we can get easy verification. Right, so if you're theoreticians, you'll look at this and you'll say, this is great. The linear proof time, that's optimal. That's the best we can hope for. And things are very compact. I mean, I wish we could have a super constant T and make it even more compact, you know, right? But that's where we are. Whereas the practitioner will probably look at this and say, look, the constants matter. And before we were comparing with linear number of exponentiations, right? But those two things are different places in terms of maturity, right? There's been a lot of engineering going into exponentiation. They're becoming more and more efficient, right? Not so much in tensor codes, right? That's a more new technique we have here. So the question is, how do those two things really compare in practice, right? And in CK proof workshop, people will talk about hardware for exponentiation. So, you know, group multiplication on elliptic curve can go down all the way to like 5 nanoseconds, right? It's really fast. Okay. And the practitioner may also say then, you know, is linear time so important? Well, maybe I could, you know, I'm fine with a logarithmic overhead or whatever you can get from other systems, right? Because that's also not so big unless it's really an enormous size of a statement. So the place where the practitioner probably helps us out is if you can get T root, right? I mean, we said, look, theoretically it would be nice to get even lower, but I don't think a practitioner would care much. I mean, T root is already pretty good for practical purposes. So I think it's a very interesting question, right? Will these strict linear time protocols also be translated into practice, and does it really have an impact, right? And I think it's interesting to compare with sort of the advances we've made early on in zero knowledge proofs, right? Where back in the olden days, right, you came with a theoretical improvement, it would typically shave off a factor security parameter, or maybe even a power of that or something like that, right? So it would really be a big advance that we could make in those days, right? And of course, that would translate directly into having significant impact in practice, right? And now we're down to a place where, you know, things are a lot more murky, right? What is actually practical, right? It really depends on, you know, what is the concrete size of the statement you want to prove, what is sort of like the properties of the computer you are running on, and all these kind of things. So there are a lot of considerations that come into play, and we cannot as easily model it as theoreticians because we're sort of like right at the edge of where the theory still makes sense, right? And we really have to be careful about the computational model that we're working on. And linear time is really fickle, right? So we had when we were working on the proof, at some point we were using said, look, and we'll sort these elements, right? And then Alessandra said, look, hey, but sorting is not something you can do in linear time, right? So suddenly that's out of the window, which in all previous cases had been perfectly fine. Sure, you can sort, right? That's pretty fast operation. And then it turned out that, well, we didn't really need sorting, and we could get things going. So this is sort of like where we are with this work. I mean, I think it's very nice theoretically speaking. We get very good theoretical bounds, and I'm just very curious to see whether that's, you know, this line of work is something that's going to make it into practice and be seen on the blockchains, right? And I guess history will tell. I don't have a conclusion here yet, but I mean, so far, I think the blockchain space has been really kind to zero knowledge proofs and really made a great effort and been very adept in taking zero knowledge proofs from theory to practice. So thank you for your attention.